Good afternoon. The title of my talk is Linear Fractional Order H Difference Equations. And this is a joint talk. I will be talking in next 19-20 minutes. Once I finish, Samuel Chang is gonna continue and he's gonna show us some graphs, some demonstrations with Mathematica. So this is a joint work with Dr. Jagan Mohan from India and Kamala Dadashova, graduate student. She graduated from our department from the MS degree in our department last year, and she is in the PhD program this year. And I also collaborate with undergraduate at the same time high school student Samuel Chang. And as I said, Samuel is gonna finalize my talk for today. I like to start with basic definitions that some of you I am sure like to see some definitions of fractional operators, as well as some basic definitions of delta and nabla. Sorry, I will be using nabla operator, nabla difference operator, and nabla sum operator. I'm going to continue with Mittag-Leffler type functions. And then I'm going to introduce you linear fractional order H difference equations. We will be talking about their solutions, and this is going to be higher order. The results are for higher order equations. And then as an application of what we are doing in this work, I like to continue and talk about an eigenvalue problem. And then at the end of my talk, as I said, illustrations will be done by Samuel using Mathematica 12. So I also like to mention that Samuel is a high school student, seen here. At the same time, I believe he is finishing college this year as well. So he's getting 2 degrees at the same time, as far as I know. So why is Hn sub A? So this is the domain of the problem that I will be introducing here. So Hn sub A. So as you see, this is a discrete domain. This is a discrete domain. But why is it here? Why is this domain my choice? Because it's a time scale. It's a closed subset of real numbers. I also see that this domain as a bridge between two things. One is natural numbers, capital N. This is the case where H and A are 1. And another one is an entire line of real numbers from A to infinity when H converges to 0. This is also a good choice for modeling purpose. Why? Because in the previous AMS meeting in October, in my talk, I talked about tumor growth models using this domain. The concentration was given hourly, and the tumor volume was measured daily. So for such, domains, we prefer using this type of discrete domain. And it worked very well for the modeling purpose and for data fitting purpose. I like to first start with introducing you the backward H difference operator. So it is nabla operator, and it is defined as f of t minus h over h. When h is 1, then you know that this is just a basic nabla operator of discrete calculus. Here I want to mention that how we do perform the higher order difference operators. So this is how we do that. And then next, I like to continue with H rising factorial power. So it is defined as this quotient, H rising factorial power. It is a quotient of this Euler gamma function. And as long as this quotient is well defined, then we do have this function, rising factorial function, well defined. And why we do need to use this? Because we like to have power rule, power rule valued for null operator, null H operator, or H null operator, I should say. So here is what power rule says. If you are performing H null operator to this factorial power, then power comes down and you subtract 1 from the power. That's how we do perform. All right, so then we do have this H fractional sum operator, and as you see, there is a kernel standing here. And the good thing about this kernel, this is a non-singular kernel. Recently, there are some papers about singular, about the concern on the singularity of the kernel, but for the discrete version, kernel is not singular, it is non-singular. That's good to have. So this is the definition of fractional sum operator for this HNA domain. And then we have here H fractional difference operator, and it is defined in the sense of Riemann-Liouville. As you see, when I apply alpha order difference, H difference operator to F, then I do first perform the sum operator, fractional sum operator to F, and then I perform the nabla difference operator. So this is known as Riemann-Liouville sense. But if you change this order of these two operators, then we do have Caputo. But in my work so far, since 2005, when I start working on this discrete fractional calculus, I use Riemann-Liouville in all my work, in all my papers. It is challenging. It is challenging to work with Riemann-Liouville definition of this fractional sum operators. Now, I also like to mention about this lemma. This lemma tells us the relation between H difference operator and discrete null operator. So if you take H as 1, you know that you will be getting null operator of discrete calculus. But there is such a relation, and this relation gets into place once you have this G function, and G is defined on this discrete domain to H and A sub A. So we have such a relation. Once we have this relation, we can also talk about the relation between fractional sum operators as well as fractional difference operators. That's what we do. And why we need this lemma, I'm going to show you one example in my presentation today, how we use this lemma to prove things in this domain, H and sub A. We have power rules, which is good. Without power rules, we cannot move, further in the story. So we need power rules. So if you just look at these two power rules, I want you to just observe what happens to the powers. Here, minus alpha, beta, you add them here. Here, alpha and beta minus alpha, you kind of subtract. So we have the power rules for fractional sum and fractional difference operators in this H and A domain. And then we do have Mittag-Leffler type function. If you have seen Mittag-Leffler function, then you know what I am talking about. Mittag-Leffler function is a generalization of exponential function, and in continuous time, of course, I'm talking about generalization of e to x function, exponential function. So this is the discrete version, and this is the version that we have in the domain H and sub A. Here A is t sub 0. And then I also want you to observe that this is not infinity. For the continuous case, it is infinity, but here it is not infinity. But when H converges to 0, then this goes to infinity, right? One of the quick observation is when you replace t by t sub 0, you will get 1 right away. That's good to know. I like to continue with telling you some properties of this Mittag-Leffler type function. The first property is about fractional sum operator. So we are applying alpha fractional sum operator to this Mittag-Leffler function. And then you see I wanna ask you to look at how the indices changes when we do this. And then we apply fractional operator, alpha fractional H operator, not operator, to this Mittag-Leffler function, and just please watch what happens to the indices. And then we have such a relation, as you see, we are seeing some delay term is occurring. So going from here to there is a lambda, and the delay term is occurring. With this property, then I am getting this nice property. When I calculate the alpha fractional difference operator to the Mittag-Leffler function, then it satisfies this side. But then, as you see, this is a kind of sign to me that Mittag-Leffler function satisfies a fractional discrete equation, right? So you can replace this by y. This is y of t minus h. So you have a discrete fractional equation with a delay. So delay is occurring here, and I like to talk about why we do have delay in our equations. So let me go back to the very simple differential equation, y prime equals lambda y. And I like to replace y prime by its Newton definition, h converges to 0, y of t plus h minus y of t over h. And then I'm going to do approximation. Once I do approximation, I take out this limit. And then when I look at this left-hand side, I do have delta h y of t. Right-hand side is same. Then I'm going to apply or maybe shift both side t h unit left. When I do that, I'm getting this first order h difference equation with delay. Okay, when you fractionalize this equation, then here is what happens. We have a theorem here. So here is the fractional version of the equation that I was mentioning. So what are the solutions of this fractional order equation? We are talking about alpha between k minus 1 and k. So we are talking about k number of linearly independent solutions here. And the proof of this, we are not repeating the proof that we have seen, the proof when h equals 1. So what we do is when h equals 1, this is true, and this was proved before. So what we do is we do use a relation between h fractional operator and just fractional null operator. And we do use such a relation that we proved before to prove this result. So as I said, this is just a quick way of seeing things, and we don't have to write the proofs for h equals 1 case and h equals in general as a two separate results. We don't have to do that. I'd like to continue and remind you about the convolution product. So when h equals 1, this is the discrete convolution product. So this is the H version, I should say. But here I also want to tell you that maybe I forgot to tell you, H is any number, H is any positive real number here. We do consider this non-homogeneous equation. This is called variation of constants formula. So when you look at the solution of this non-homogeneous equation, then the solution, you have k number of linearly independent solutions plus for the non-homogeneous case, you have this convolution product gets into place. Now I'd like to continue with an example, with an application of what we are doing in this paper. By the way, I am talking about a paper which was just published in December in International Journal of Difference Equations, honoring Professor Johnny Henderson. So, but in the fall semester, I worked with Samuel as a research assistant. So he helped me to visualize things, what I am doing in this paper. And then we also we came up with other ideas to look at in spring semester. So here is the boundary value problem we have here. And here are the two linearly independent solutions. The first theorem that we have here is lambda element of R is an eigenvalue of this one, two boundary value problem, then lambda must be negative. Okay, then I do remove lambda and I replace lambda term with this mt minus h function. When I do that, then next I calculate the Green's function here. But in our work, once we have this Green's function, we want to see how it looks like when h converges to 0, or how it changes when alpha is between 1 and 2. So you are gonna see some graphs in next few minutes. Samuel is gonna talk about the graphs. And then here I'm writing the boundary value problem 1 and 2 as a sum equation. Once we have the sum equation, then we do write it as a matrix equation, kind of vector equation, I should say. Here, capital G is a square matrix, and all the entries are elements of this Green's function. And then we have this nice theorem. So, in order to calculate the eigenvalues of the boundary value problem 1 and 2, you just need to calculate the eigenvalue of this square matrix. But h lambda to the negative 1 eigenvalue of the square matrix, if this is the eigenvalue, then lambda is the eigenvalue of the boundary value problem 1 and 2. And we are going to demonstrate this result with mathematical, and as I said, Samuel is going to do this. Samuel is also going to show you this n by n matrix where n is 10. So he's going to show you 10 by 10 matrix G, and then he's going to calculate lambda values for this G to get the lambda values, which are called eigenvalues for the boundary value problem 1 and 2. And then he's gonna finalize his demonstration with eigenvectors, of course. Once you calculate the eigenvalues, then you plot them back in the equation to get the eigenvectors. So let me ask Samuel to continue with his presentation. Then if you have any questions, you will let us know at the end. So let's see how the demonstrations will go.
Dr. Atici's asked me to talk sort of on the computational and the visual graphical things we've done for our models. So we compared basically discrete and discrete fractional approximations and continuous fractional and discrete fractional approximations during our computational aspect. So Here is the most simple of the Green's functions that we compared, the difference between discrete and discrete fractional. So on the left-hand side, you'll see a discrete graph, which is in blue on the left-hand side, where alpha value equals to 2. And on the right-hand side, you'll see a discrete fractional case, where the alpha value moves between 1 and 2. And in red there, you will see the same graph you see on the left. So if I play that approximation, you will see that as alpha value approaches 2, the discrete fractional case approaches the alpha equals 2 discrete case that we saw on the left. And theoretically, when it touches alpha equals 2, it should be identical to the discrete case. So in this next aspect here, we have a matrix eigenvalue definition, and we defined each of these by the Green's functions we talked about right before. So we defined each of these. These are 9 by 9 matrices when n equals 10 because they are n minus 1 by n minus 1 matrices. And we'll see that they are symmetrical as we expected along the diagonal from the top right to the bottom left. So if you fold them over like that along this diagonal, for both models here, both discrete and discrete fractional, they will be symmetrical. So for this next portion, we did a one-dimensional eigenvalue visualization from that matrix that I just mentioned. We took the values out and graphed them on a one-dimensional number line here. And for this one, I graphed many different ones between alpha values of 1.7 and 2. And so we set n as 30, h equals 1/30th, which is the reciprocal of n. So for any h and n really, as we move towards the continuous case, the best approximation is going to be the one with alpha value closest to 2. And it is still dense on both sides, unlike the continuous, which is only dense on one side. But they do approximate better as alpha approaches 2. And you'll see on this right-hand side, the initial values are not 0. They are listed on the right-hand side here. They're not 0. It just looks very close to 0 because simply of the nature of the scale of this graph. And the next one here, we changed h instead of alpha here. So the h value here changes from 0.01 to 0.05. And again, we see the best approximation of the continuous case is when the h value equals 0.01, or when it approaches 0. So technically it should get closer and closer as this h value gets even smaller with the continuous case here. So the next thing we did was we compared the continuous fractional function with the discrete fractional function. The continuous fractional is defined as the Mittag-Leffler function with two forms here, one when alpha is less than 1 and one when alpha is greater than 1. And here we have a nabla with delay, which represents our discrete fractional function. And I mentioned that as the E function because the notation is an E. So the E function visualization here, I have all of these right here on the right-hand side, these colorful discrete graphs on the right-hand side. These are representations of different h values when entered into the nabla with delay, or the E function. Whereas this one I've denoted, especially right here, is the continuous fractional Mittag-Leffler function. So the discrete fractional E function gets closer and closer to an approximation of this continuous fractional model when h approaches 0, similarly to what we saw with the continuous versus discrete fractional one-dimensional number lines before. However, when we change this h value to greater than 1, and we use this form of the Mittag-Leffler function that is with h is greater than 1, then what happens here, or when alpha is greater than 1, what happens here is we get an approximation of the continuous fractional that lies between an h value of 1.2 and 1.3 with this new function right here, with this new form of the function. So this lies between those two. And last but not least, we have our eigenvector visualization. So we computed eigenvectors based on the eigenvalues in those matrices you saw earlier. And they are very similar between the continuous and the discrete fractional cases. You'll see that each of these, there are 10 on each graph, and you'll see that the only difference between the right-hand side and the left-hand side is the amplitude changes. So you'll see here we set alpha equals 1.99 to make it a closer approximation of the left-hand side. And so starting with the third jump right here, starting with this light green, you'll see that this one goes, in amplitudes gets greater and greater with every loop that it makes. So whereas this one, the amplitude stays between -1 and 1. So thank you very much for your time, and feel free to contact us later with questions or ask them now. Thank you very much.